For over 70 years, a four-engine heavy bomber lay hidden in just 50 to 60 feet of water off the southern coast of Sweden. The aircraft is a Handley Halifax Mark II, bearing the serial number HR871, originally assigned to the Royal Canadian Air Force 405 Pathfinder Squadron. A large object was detected around 2011, and later survey and dive work helped confirm that it was Halifax HR871. The site created an immediate operational paradox. A wreck at this depth should have been within reach of marine traffic, commercial sonar, and standard recreational diving. Yet sand, seabed contours, and scattered exposure prevented the aircraft from presenting a clean outline. When the Swedish dive group known as Havsresan from Lund University later examined the site, they found a partly buried debris field rather than an obvious shallow water bomber. That delayed recognition complicated the first hard question facing the recovery team: whether enough usable structure had survived for the Bomber Command Museum of Canada to complete a full-scale rebuild. 70 years submerged in a coastal zone usually guarantees the total degradation of thin aviation metals. An aircraft resting in shallow water is normally subjected to destructive wave action, tidal currents, and intense biological incrustation. The requirement set by the Bomber Command Museum of Canada imposed a stricter threshold than a standard accident investigation. A forensic crash investigator only needs enough metal to read a fracture surface or identify a serial plate. A museum rebuild needs physical mass, including intact spars and surviving engine blocks that can safely support their own weight. Rebuilding a heavy bomber is a demanding exercise in structural geometry, so the 2015 assessment had to answer a single practical question: whether enough connected, extractable structure remained to support a full-scale museum rebuild. The identity of the aircraft as a Handley Halifax Mark II made that question unusually consequential because very few of these four-engine bombers survive in any recoverable state today. The investigators faced a distinct procedural boundary. They knew the confirmed location and the confirmed identity of the aircraft, but the actual condition of the metal remained highly uncertain. The recovery team had to transition from the initial discovery phase to the cold calculus of underwater salvage planning. That uncertainty shifted the story from location and identity to the cause of the loss. What mechanical failure brought a four-engine bomber to this specific coordinate after its crew was already gone? The simultaneous loss of two power plants created an irreversible operational boundary. On August 3, 1943, the heavy bomber entered a severe thunderstorm cell, and a lightning strike knocked out the two inboard Merlin engines while also crippling radio, electrical, and instrument systems. Because the failed engines were both inboard, the problem was less a violent sideways thrust imbalance than a brutal loss of power and controllability. Attempting to cross the open water back to England under those conditions made the odds unacceptable, so the safer operational decision was to divert toward neutral Swedish territory and abandon the disabled airframe before the situation deteriorated further. An aircraft structure can conduct lightning energy through bonded metal paths, wiring, and attached systems, but the exact path of the current through HR871 cannot be proven from the surviving public record. After the crew escaped, the abandoned heavy bomber ultimately struck the surface of the Baltic Sea and sank to the seabed. When an aircraft goes into a marine environment, the primary threat to forensic recovery is not the physical impact, but the subsequent chemical degradation. The recovery team analyzing the site decades later had to judge whether any surviving structural material was strong enough to handle careful excavation, rigging, and lifting. This recovery feasibility depended heavily on the local marine chemistry, the amount of burial in sand, and the condition of each individual component. The wreckage settled into the Baltic Sea, a body of water defined by extremely low salinity. Salt water destroys submerged aircraft through galvanic corrosion. When dissimilar metals like aluminum structural frames and steel engine mounts are submerged, the salt water acts as an electrolyte, allowing ions to flow and rapidly dissolve the weaker metal. Because the Baltic Sea contains brackish water with relatively low salt content, the fluid acts as a weaker electrolyte than open ocean seawater. This chemical environment can slow galvanic corrosion, but it does not stop it. Chlorides, oxygen, mixed metals, currents, and time still attack the aircraft. The preservation advantage is relative, not absolute. The condition of the sea floor provided a second critical protective mechanism. Shifting sand buried major sections while leaving heavier or higher parts exposed. Where it packed into the wings and fuselage, it reduced currents, oxygenated water, biological growth, abrasion, and unsupported movement. That mechanical stabilization worked alongside the relative chemical advantage of the brackish water. The material strength of the aluminum was preserved far beyond the expected timeline for a 1940s aircraft, giving the recovery team a real chance to target intact structural frames for the museum rebuild. That preservation advantage created the next constraint. The hidden sections had to be mapped precisely before they could be touched. When an aircraft is deliberately abandoned after a damaged approach toward neutral Sweden, calculating its final marine resting place requires a reconstruction rather than a fixed mathematical curve. The crew had been at roughly 4,000 feet during the approach, but the exact altitude at abandonment and the final descent profile remain uncertain. The pilot trimmed the heavy bomber for a steady southwesterly glide before ordering the crew to bail out, leaving weather, engine drag, damage, fuel state, and attitude changes to shape the uncrewed descent. The result was not a point target, but a complex linear debris field 15 kilometers from the coast. Locating that distributed field decades later required the team to treat the site as a fragmented, partly concealed archaeological problem rather than a simple salvage grab. The spatial relationship between wings, fuselage, and detached components had to be rebuilt through disciplined mapping, not visual recognition. Before any physical extraction could even be considered, the recovery team had to mathematically isolate and divide the hidden debris field. Blind underwater digging would destroy fragile spatial evidence and risk catastrophic shear damage to the targeted aircraft components. To control that risk, the dive team established a rigid 50 by 50 meter physical grid over the presumed location, laying measured boundary lines and fixed datum points on the ocean floor. The grid transformed a chaotic buried site into a controlled reference matrix, forcing every submerged structure to be plotted before excavation began. With those coordinates fixed, the map became the bridge between survey discipline and physical excavation. How do you expose a buried airframe without ripping the metal apart? Removing massive volumes of sediment from a fragile airframe forced an immediate operational trade-off. Standard heavy salvage clamshell buckets could clear thousands of cubic meters of sand rapidly, but their mechanical force would crush 1940s aviation aluminum. The recovery team therefore needed a non-destructive extraction method from the specialized salvage vessel River Thames, remove the surrounding seabed material while keeping lateral shear off the ancient airframe. To solve this handling constraint, divers deployed large underwater vacuum hoses to clear the massive seabed overburden. The system pumped highly pressurized water down to the sea floor, creating a localized low-pressure zone at the intake nozzle. That pressure differential pulled surrounding fluid and loose sediment into the pipe, lifting the heavy slurry up and away from the work site. By hovering the intake just inches above the buried object, divers could remove sand while keeping the force fluid, distributed, and controllable. Managing this industrial equipment from the deck of the salvage vessel River Thames required extreme procedural discipline from both the surface operators and the submerged dive teams. The sediment covering the heavy bomber was not always loosely deposited. Decades of current action and burial had compacted parts of the sand into a dense matrix. Extracting a complex aircraft frame from that matrix required balanced material removal, not pressure equalization. If a diver cleared one side of a structural section but left the opposite side buried, the unsupported metal could bend, twist, or tear under its own unbalanced load. The dive team sequenced excavation passes layer by layer across the entire worksite, reducing the sand uniformly so no single frame was forced to carry an asymmetric load. Thousands of cubic meters of spoil also had to be discharged far outside the immediate footprint. Otherwise, coastal currents would wash the material straight back into the freshly dug trench. Operating the massive underwater hoses introduced a severe secondary limitation regarding visibility. The powerful suction forces disturbed the very fine particulates locked within the seabed, instantly creating zero visibility conditions around the divers. Working in a total blackout environment meant the submerged team had to rely almost entirely on precise tactile feedback and rigorous buoyancy control. They had to maneuver the heavy, vibrating suction hoses precisely around jagged, torn metal edges without actually seeing the physical hazards. The surface crew on the salvage vessel River Thames monitored the massive water pumps continuously, regulating the exact amount of suction pressure delivered to the sea floor. Too little pressure and the dense sand would not move. Too much pressure and the hoses could accidentally inhale smaller, critical mechanical artifacts scattered around the main wreckage. Exposing the wreckage solved the primary access constraint, but it also forced the next decision. Which pieces had enough internal strength to survive a controlled lift through the water column? They had to evaluate the uncovered bomber and decide which pieces possessed enough internal strength to survive a mechanical lift. A vintage aircraft structure relies on a continuous internal load path to distribute its own weight across its span. After more than 7 decades submerged, the connective rivets, wing roots, and primary fuselage bulkheads were heavily compromised by impact trauma and localized metal fatigue. Attempting to raise the entire bomber as one contiguous unit would have caused the weakened fuselage to buckle and shear under its own unsupported mass. The team therefore abandoned full-frame recovery and isolated only discrete, structurally robust sections that could act as self-supporting lift modules. The salvage engineers systematically surveyed the debris field to identify components that could handle direct rigging. They bypassed the highly fragmented fuselage skin panels and focused entirely on the densest elements of the wreckage. The primary targets became the massive Merlin engines and the heavy structural core of the horizontal tailplane. A Merlin engine is a compact, heavy assembly of aluminum alloy castings, steel liners, shafts, gears, and other dense mechanical parts. Unlike the thin aluminum outer skin of the aircraft, the power plant retains much of its rigid geometry because its mass is concentrated around thick castings and heavy rotating components. That compact mass can make an engine a more practical recovery target than torn skin panels, provided the rigging is designed around the actual condition of the wrecked assembly. Before calling for the surface crane, divers had to inspect the engines and surrounding attachment points to judge what could actually take a lifting load. Once a safe rigging plan was confirmed, the recovery divers could secure the engines with appropriate lifting gear, spreading the load so the wrecked assemblies were not crushed, twisted, or torn apart during the primary lift phase. The main spar of the horizontal tailplane carried a different kind of value. A main spar functions as the primary load-bearing backbone of any structural flying surface, engineered from thick, extruded metal designed to withstand massive aerodynamic bending forces during active flight operations. That inherent thickness meant the spar retained enough baseline tensile strength to survive the mechanical pull of the salvage crane cables. Extracting a long structural component required rigorous center of gravity calculations. Rigged off-center, it could tilt vertically during ascent and slip out of its securing straps. Securing this tailplane section was vital for the museum rebuild objective because it provided a verified geometric baseline for rebuilding the rear structure. Together with the engines, the recovered hardware reinforced the identification and gave the museum authentic material for the rebuild effort. Hoisting these selected heavy components from the sea floor to the surface vessel required precise cable tension management. As a submerged object moves through the water column, it benefits heavily from natural fluid buoyancy. The moment a heavy Merlin engine or a long tailplane spar breaks the surface of the water, that supportive buoyancy vanishes instantly. The sudden transfer of the full static weight onto the crane cable creates a massive shock load through the rigging system. The salvage crew had to hoist the components at an extremely slow, tightly controlled rate to manage this dynamic weight transfer through the splash zone. If the lifting slings shifted or slipped as the parts breached the surface, the swinging heavy engines could easily crash into the deck or crush the more fragile aluminum sections staged nearby. Only the most viable pieces were subjected to this harsh mechanical transition. The selective lift succeeded without causing secondary destruction. The massive power plants and the critical tailplane spar were secured on the deck of the salvage vessel. The ancient metal had survived the transition from seabed to open air. But would 70 years in the Baltic alter how the extracted wood and metal had to be handled once exposed to oxygen? Once the recovered components reached open air, the next proof limit appeared immediately. The team had secured heavy power plants, critical spars, and a completely intact Rotol laminated wooden propeller blade, but survival on the deck did not guarantee survival in the atmosphere. The immediate chemical threat now dictated the entire post-extraction workflow. The same conditions that slowed underwater decay became dangerous once the wreckage met oxygen-rich air, triggering a rapid acceleration in material breakdown. The recovery team cannot simply place the extracted components onto a dry transport deck and walk away. If the salvaged aluminum frames or the wooden propeller blade are allowed to dry out naturally, the residual marine salts trapped deeply within the porous material will begin to crystallize. This internal crystallization process causes rapid physical expansion. The expanding salt crystals act like microscopic wedges, literally blowing apart the delicate internal layers of the laminated wood and drastically accelerating the total deterioration of the ancient metal skin. To reduce this rapid structural risk, the salvage crew must implement strict conservation protocols as soon as the artifacts are secured. Newly exposed artifacts are kept wet rather than allowed to dry uncontrolled. Upon reaching conservation facilities, vulnerable components can be transferred into controlled freshwater baths or other treatment systems. This soaking process gradually leaches destructive salts out of the materials over an extended time frame. The water chemistry is monitored and refreshed until salt levels fall to a safe, stable conservation threshold. Only then is the latent corrosion and crystallization threat reduced enough for the next stabilization phase. The Rotol propeller blade presents a particularly severe handling constraint. As a highly organic component, the fully waterlogged wood requires rigorous, heavily monitored stabilization. If the ambient moisture evaporates too quickly, the cellular structure of the original wood will permanently collapse, causing irreversible warping, splitting, and structural disintegration. The conservation team must execute a highly precise drying phase where the internal water is slowly displaced and replaced with specialized chemical stabilizers. This meticulous process ensures the propeller blade maintains its exact original aerodynamic geometry and physical density. Once the desalination and stabilization processes are certified complete, the preserved aviation hardware is fundamentally secure and safe for international transit. The heavy engines and the long tailplane spar are meticulously braced, crated, and prepared for a complex logistical transfer. They are shipped across the Atlantic Ocean, maintaining a strict chain of custody until they finally arrive at the Bomber Command Museum of Canada. At the museum facility, the extracted hardware is not simply treated as isolated historical debris. It becomes reference material, display material, and authentic restoration evidence. Rebuilding a heavy bomber requires dimensional accuracy, and original components can help restorers understand real geometry, rivet patterns, fittings, and load paths that drawings alone may not fully communicate. Their role should not be overstated without a confirmed structural design. By systematically overcoming the constraints of the marine environment and applying careful conservation, the investigative team secured critical material without asking the recovered components to prove more than they can support.